Welcome back to our lecture series on neural networks for architects. We are on day 4 and our first chapter is on functions, layers, chains and graphs. So we are about how to set up and construct or how to code neural and specify neural networks. So let's have a look how this is working. This is day or book 4, set up neural networks. You always start the cloud notebooks with this button here, and it got interactive. This is our chapter, this is our day. Good. There's a lot of stuff around in YouTube explaining what is a neural network, so how does it work, and not what is. What is a neural network, to kind of get an understanding what it is, and they try to make it intuitive. So most prominent, I think, is this link here with 9 million views. Look it up. But be careful, it's not on how to do things. It's about thinking differently, and you have to learn to write or to talk about it instead of, and it's not a thing that you get intuitively, it's a question of your imagination. So it's just the other way around. You have to put yourself in a position of an alien out of time, and intuition is within the reality of time, and this is blocking the understanding of what all this is about. So neural networks are built with layers. Layers are organized in sequences or interconnected in networks. So we will see how this is done technically, how you write about on how to articulate and specify a network by code. So unlike functions, these layers are functions are within the reality, so they're kind of production lines, they're predicting. Layers are at the edge of the world. So therefore you always have the thing that you encode, so it's a kind of view from the outside of the world. That's the encoder. Then you rationalize the views, and then you talk back with decoders towards reality. So, and how this is implemented? This is implemented in functions, and they are directive in time. And layers, neural networks are implemented with. They wrap functions and give additional features to functions. Therefore, it's a good idea to get an understanding how all the neural networks are anchored towards the very principles of the computing language. So, this is how functions work in this environment. You always have an expression. This has a header and a body, and then you evaluate, you rotate this symbolic structure, and then it produces a result. So always first this, then that. So there's an infix notation. This is the full form, and this is another notation to get it more convenient. But everything is like this. Written is a little different. If you want to make your own function, this is a way how to do it. You have the a symbolic name for function. The convention is that it's a capital letter at the beginning. It's not needed, but so. Then you have to specify the body of the function with parameters. And then you assign an arithmetic structure towards these, a structure towards these parameters. So if you did that, it works like expected. So you can also do, for example, then let's no. So there's another notation for the same thing as we had it here and with towards here. This is a call of a function, and it works the same. So it's apply this number to the function. This is how to read it. So, and this is this symbolic name of the function. Map apply this list, each element of the list toward this function. Therefore, it's adding 3 to each element of the list. So you can do that without the parameter names and assign a pure function without named function, assign that to a symbol. So then I would say it's most proper not to have a capital letter for this symbolic name, but it works the same. But this is a kind of implementation as a pure function. And of course you can map, apply a list to this pure function as well. And you even can skip the symbolic name of this. Simply takes a pure function and apply a value. Or this is very, very often like this, have a pure function, map, apply a list of values to that to do this. So this is a kind of recap because this is a form the layers in neural networks are using. And if you want to get an introduction into the Wolfram University, there is a nice introduction to the Wolfram language. Take chapter 25, for example, to get the discussions around these concepts I introduced and discussed here. Good, that's with the what is a function. So now that's a very simple turn. We just get a symbolic name to wrap a function. So, and we call that element-wise layer, and this is we assign this element-wise layer to the symbol layer. So, and then this shows up like this, and this is a function which can do more than a few pure functions. So it's a layer, and this is an element you're building your networks with, a simple element. You see all the different parameters. One of that is a parameter, is the function. Then you have an input as an array, output as an array, and so on. We assigned that to this symbol, and this symbol can run as a regular function. It works different from a function directly with lists of values. You don't need the mapping that's included. And it works on any dimensional arrays. So in this case, a two-dimensional array of points, and it adds simply, it applies the function to every element of these lists. So that's how layers wrap functions. So let's go one step further and make the most simple network. So I told you, you have reality, encoders, edge of the world, then there is a network. We want to have a single layer network, and then the talk back with decoders and having it back to reality. In this case, we simply want to have an encoder for an image. Whatever is coming in, we want to read that as an image, resize it to 32 by 32, and put it to a color scheme of RGB. So we discussed that in the yesterday. So this is our encoder. We assign that to encode, to this symbol. The way back from the edge of the world to reality is a decoder on image. We take an array of data and just render it as an image to reality. We can do it as a sound. We discussed all this. Good. Now, this is an image. Load that from the cloud. Gerhard Richter, cloud. This is not, it's too heavy having that in the notebook in the cloud, so just the symbolization is good. So, and now we can say encode the image as discussed yesterday. This is a code, and then we look for the dimensions of the code. It's just a lot of structured data. It's 3 colors, x, the width and the height of the image. So these are about 3,000 numbers. So if we want to get the production line of the decoder, so then the image goes to the encoder, and that goes one-to-one back to the decoder, which means we put the image, encode it, and then stalking back to get the image in 32 by 32 in RGB. So now we implement our, so it's simple like that. Now we just, instead of image, encoder, decoder, image, we just put in our network. In our case, is this simple layer, adding 0.2 to each element, as we had it here, to each element of a list. We had it here. We just add 0.2 to each element of an array. In this case, it's a 3-dimensional array with colors and width and height. So therefore, image to encoder, to the layer, to our network, and then decode. And this makes an addition, a brighter image. So that's it. All neural networks in Mathematica and elsewhere are thought like this. So that's simple. Now it's written differently to get a more visual understanding of what is going on. So this is a habit of the community. So that's the same thing. So we say it's a chain. A chain gets the first element of a body gets our layer. It's a single layer chain. Then we have the input and the output. Let's evaluate that. Then we get this interface here, and we see what's going on. Input is an image. This is towards an array of 3 because of our encoder, 3 by 32 by 32. Then we go with our pure function with the brightener, the same size, and then with our decoder we render it back to an image. We can go to detail and see the input port of the layer is this size. Then this function is applied to each element of this element-wise layer. Element-wise layer says each element of this array applied with this function, give it back, done. That's our chain. Apply it to the image, very simple then, because net now is all this. This is the net, and therefore it's working, giving the same result. So, and then you, of course, you can, instead of having these things here symbolized, you can make that symbolized, you can make that explicit with these definitions. It's just the same result. Yeah, and will work as the same. We assigned it here. You can check it. Gives the same result. So there's a lot of predefined layers there's a kind of repository of layers of neural network. Here you see basic layer. This is our element-wise layer. This is the documentation. You see application. So you can read more complex networks. We will have it later. What you can do with it, a huge amount of stuff, and there's a bunch of possibilities which you have there, and check it. Whatever, extract, flatten layer, whatever, convolution layer, whatever. And it's expanding very fast, version by version. Good, look it up here. And now we apply a second layer just to show you this. So with an edge chain, the first is the list of layers. So we had this element-wise layer, and now we introduce a transpose layer, in which says we want to change x and y, or the width and the height of the image. We exchange that. It was color, width and height, and we changed it 2 and 3, which means the picture turns by 90 degrees. So if we evaluate that, we have a chain like this. We have an input toward this array. We apply each element of this array our pure function, and then we apply this layer to change the second with the third dimensions to rotate the image. This keeps the size the same, and then we go to the output, render that as an image, and this looks like this, which is a rotation of this. So, done. Simple. Good. Next, with the graph. This is not working properly on the cloud, so we have to put it here. A graph. Instead of a chain, we have a graph, and a graph contains different chains. So, and this is implemented like this. So we have the input, as we'd seen. This is defined here, as we had it with a chain, no change here. The output is the same here. You can check it here. That's the output. What we inherited from our previous example is the two layers, 1 and 2. 1 is the element-wise addition, brightening of the picture. 2 is the transpose layer, change width and height of the picture. So that's this. What is new is we introduce as a second element of net graph, we say how are these layers connected, and this simply says the port input goes to 1, which is the brightener. This output of 1 goes to the input of 2. Input is here. This changes x and y, gives it to the output. This output goes to the net port here, which is input, image, output, image, and then gives it to the decoder and shows it. So this is the same as we had before, but the connections of the layers is explicit, and there will be a list of, so this is one chain, you can have multiple chains, which is then a network. Having that, we simply can say net of, and the image, we need the image, copy. This is the image, net of image, and this is just our production line changing the image. Good. Now we go and introduce a second chain within the graph. Let's have a look. So this is what we had, the two layers. We have the input. We have two outputs now, the same decoder. And here we have two chains. So the first goes from net port to R1 to the output. So it just takes the element-wise layer. And then the second goes from 1 with the transpose layer to the output 2. So get this here. Then we see the graph of it. Input, element-wise layer brightening up. See that, rotate that, see that. So then you see how it worked. Input to 1 to output, input to 1 to output 1, then 1 to 2 to output 2, 1 to 2 to output 2. So we have two lines, 1 and 2. Therefore it's a graph. Is how to implement that. And if we call that, let's make it like this, we see two outputs. The first output is this, and the second is a rotated one. So it's like a production line, as you might know it from Grasshopper. Now get two outputs, the same thing. Yeah, let's check it within the graphics. So here, input, image 1, image 2. We add these, we add these layers. So one by one we add image. This is a threading layer plus. So we simply add all the pictures and make an overlay. Then the color range of that is of an image is 0 to 1, of two images 0 to 2, and therefore now we have to get a pure function to divide it by 2 to get the combination of two pictures to 0 and 1. So as we had a pure function, just half, calibrate the colors again, and then this should go to output, then this should go to the rotation and to the output. We have that here, these three layers. These are, this is the first line. This says the list of port 1 and port 2, these are 2. They go to 1. See it here, that goes to 2, and that goes to output 1. That's the first sequence. The second sequence is you anchor it here, you go to 3, which is the rotation, and that goes to output 2, which again has this decoder. So having that, then we have to load the two pictures. Taking that off to see the pictures. So it's Richter, the cloud, and the sea. Because of the encoder, putting it to 32 by 32, we don't have to bother of the format and of the color space. We don't have to bother around with that, because of our encoder is able to do that. Then we simply say net image 1. Let's get rid of this image. We don't need that anymore. So image 1, it's here. Image 1, that's an association, goes to image 1. Image 2 is image 2, that's the second one. And that's it. So these are the two inputs. All this is then automatic. And this produces two outputs, here and here. If we want to access one, this is an association. If we want to have then we go for output 1, and we want to see that, then we have the output 1. And if we want to go for output 2, we get it like this, the rotated one, overlay of two pictures. That's it with how to set up the interplay of functions, layers, chains, and graphs. So it's still in a production line, so the idea is still be in time. So you have input, then you produce in a very specific way, in a systematic way, an output. And the next chapter on training, we will put that to the edge of the world and start to rotate this in the realm of the ratio instead of the real. This will be training the network. See you then, and that's it. Thank you for watching.